As I was saying before, I forgot to start recording. We're going to test this model against two other models. So you should record. The only reason I remember I saw Aaron taking pictures, like, why is he taking a picture? Oh, I better make sure that I'm recording this so he doesn't have to take a picture. 9.47 or 947.15 chi-square, 131 degrees of freedom, and a scaling correction factor of 1.3914. We're going to test this against two other models, right? So we've written these numbers down. Let's test it against our first alternative model. And the first alternative model says that all of these things load on a single factor, right? We're going to do this. We're going to do that. In fact, what we're going to do is this right here. I'm going to copy this for right now because I don't want to lose this. And we're just going to go like such. So this is a single factor. All of the alls loading on one factor, and we're going to allow this. We've allowed this to correlate in our structure. We're going to continue to allow it to correlate in every other structure, unless it causes us issues. And by issues, sometimes you will correlate something and it will say like the residual factor covariance matrix is not positive definite as it should be, in which case it's because of the factor that you, or the item that you just correlated, and you have to go back and uncorrelate it because it messes with your factor structure. We probably won't run into that, but if we do, then we'll deal with it then. This is what it looks like, nice and fancy. 18 items all loading on one. Who's got their chi-square table handy? 2,802. Let's look at our model fit. 134 degrees of freedom. RMSEA is 0.101. Is that good or bad? Bad. CFI? Bad. SRMR? It's 7, so it's probably bad. We want at least 0.06 or less. Preferably, like I said, preferably below 0.05. 0.03 is better. Anyway, somebody want to write down this chi-square for me? And I am going to pull out my little calculator here. And so what was our last chi-square? Minus, I'm sorry, say it again. 947.15. Okay, so that is 1855.468. Somebody want to write that down? 1855.468. And what were our degrees of freedom before?
131.
So a degrees of freedom difference of 3. I wonder if those will be significant. Let's check out a chi-square table. Let's just pull up any random one. This is fine. This one looks better. Okay, so we have 3 degrees of freedom at a p-value of 0.05. That means our cutoff is 7.81. Our difference has to be at least a value of 7. How close were we? What was our difference in chi-square value? 1,855 or something, right? So that's greater than 7. So we can conclude, based on that chi-square difference test, that our model fits better than a single factor structure model, right? However, there's a problem. And it's this, that when we're using MLR, we can't use traditional chi-square difference testing. They provide, the Muthans provide the formula for calculating a true chi-square difference test, correcting for that bias. There's another discussion of it here, which provides a bit more detail in doing such. Huge pain in the ass to calculate that out by hand, just FYI. Let's flip back over here. When we recorded this chi-square, we have 2802.618, 134. Somebody write this down. and then a scaling correction factor of 1.4198. Okay. The easiest way to do this is to go to this website right here, which I love. So we have a nested model. This is a model within a model. This is our first model that we ran. What is our original chi-square value?
947.
9.15. Degrees of freedom was 131. And what was our scaling correction factor?
1.3914.
Our other chi-square was what?
Did you type that correctly?
That's what I have.
1.3914?
39. Oh, 14. I'm sorry. Okay, our other chi-square value was
2802.62.
2. Degrees of freedom was 134, right? Scaling correction factor
1.4198.
for 1.4198. All right, calculate. Oh gosh, you know what? I'm sorry, I did this wrong. These two should be flipped. The comparison model is our first model. So let's do this. Let's just copy these down, and somebody's gonna have to read that other one off to me. If these values are negative, then you know that you did something wrong. All right, read this to me again.
2802.62. 134. And 1.4198.
Okay, there we go. That looks right. So we have a Sator-Bentler chi-square difference of 1,000.521, 3 degrees of freedom, and this is using the kind of correction factor that we have, 3 degrees of freedom. The p-value is pretty substantial, and so we can conclude from this that there's a significant difference between those two, and ours is better, right? Our chi-square is lower, our model fits dramatically better. Okay.
It's called a nested model, not because what we're testing is a nested model.
Right. Yeah.
It's just what they.
Right. Yeah. It just calls it that. You have to know that your model is nested, and in this case, they are nested, but it's not. There are examples where the models are absolutely not nested. Nested means that you can develop a similar factor structure by simply adding, like, if you with the factor structure that we had with the all of the higher order factors, you could constrain that to be the exact same as the one factor model by constraining every correlation amongst the factors to be 1, which would set all of those factors to be equal, and then only constraining and then removing the 2 factor loadings that are constrained to 1. And then that is an equivalent model. Statistically, it's an equivalent model. So they are, do you understand what I'm saying when I say that? So if you have this factor structure, and these are correlated, right? You allow those to vary, and then this is constrained to 1, and this is constrained to 1, and you fix this to 1, and then unconstrained this, then that model right there is equivalent to mathematically, it's equivalent to this model with one path constrained to 1. So this model is nested within this model, right? And it's just that by freeing this and constraining that, you wind up actually having a new model that is nested within this other type of model. So you'll have differences in chi-square in known observation, or I mean in non-estimated observations. So you only have one variance here. You have variances there, right? So all right, let's keep moving. Let's test our second model. Our second, so we don't need to worry about this model anymore. We're not going to try and control for it or I mean, come back to it at all, because we already know that our model is better than that one. Shoot. All right. Somebody help me out here. F1 by alls what?
1, 3, 5, 6, and 7.
F2 by alls
4, 8, 9, 11, and 14.
and F3 by alls
2, 10, 12, 13, and then 15 through 18.
Okay, and then we are going to do F4 by F1, F2, F3. And this is testing a higher order factor structure, right? And what did we say that we wanted with this higher order factor structure? When we look at model comparison, is this model going to fit better or worse than our last model? It's going to fit better, right? At least a little bit better, at least qualitatively better, right? That is what it should look like, roughly. Oh, wait. These are no longer correlated. Let's see how this looks. We'll go back and we'll correlate those factors, but this is going to fit basically exactly the same as our last one, right? In order to, and that's because we did not correlate those factors. And that's what I meant when I said that it's nested within this, when I drew this up here, right? So is this what we had before? 947, 1.5, or 947.151. Okay. Okay. I'm not positive that this will actually run. Let's have a look. So now we're allowing those things to covary and saying that there is a higher order factor structure here at play. Shoot. It didn't run for us. I kind of figured that might happen. Say that again.
All the quotients are one thing. Maybe it's wrong. That's covariance.
Oh yeah, they should be one, you're right. Let's have a look at this. You know what? I was mistaken. Because if you add those correlations, then what you're saying is that everything that isn't accounted for in those is going to be equal to 1. So, yeah, I guess I was wrong here, and this is why I should have run this before class. These are completely nested within each other, right? It is a perfect depiction of these. So, in your homework, when I ask you to compare the higher order to the non-higher order, it's not going to make any sense because statistically they're equivalent models. One is just allowing for, instead of correlations, for all of those relationships to be driven by a higher order thing, and that higher order thing is going to be equal to the correlations that you would see between all of these variables. In fact, let's look at that. If we do, I'm not positive if this math will work out. It seems like it should in my head, but we'll see. It's not going to be perfect. No, I was thinking that possibly the association between F1 and F4 would be, well, it might be equivalent to the sum of the squared correlations of F1 with F3 and F1 with F2. And I don't know that that's actually quite the case, though. At any rate, there is no way to statistically test these, I suppose, which is frustrating. But I guess that's the way that it is. God dang, I wish I would have done that ahead of time because in my mind, there was a 1 degree of freedom difference between these two. As I started drawing it on the board, I was like, these look like they're the same though, and they are the same. So I guess what is the answer here when it comes to whether or not there's a higher order factor structure or not? What do you guys think? How do you then make a case for that? I'm going to be honest. I would have to go and read a little bit on this because I'm not sure right now. I'm going to tell you what I would guess, and that would be that theory would drive whether or not there's a higher order factor structure, right? There's the possibility of doing something different, which is called a bifactor structure. Have you guys heard of bifactor before? And okay, so what's the bifactor structure?
Basically, there are 2 different factors accounting for like variance and like different observed.
Yeah. So what a bifactor structure would be, and this you definitely can test, is you would have F4 by alls 1 through alls 18, right? And so this, put it over here. Usually when you see these, you'll see them look something like this, right? Have you guys seen something like that before? It's I think more common in like developmental research. Isn't this moving over here? I don't know how well this fits, and maybe this is actually the right answer here, but let's see. Nope, that won't work either. All right. We are not going to worry about the higher order factor structure because obviously we can't test about this, and I feel foolish for trying to bring it up. Oh well, shit happens. Yeah.
So if your theory says there is a higher order, or if your theory says there isn't, you can't prove it wrong.
You can't.
Because the models are the same.
Yeah.
So even though you base it on theory, like it's not like falsifiable.
So it's falsifiable if the higher order. So actually, let's do this. Well, so the UPS P has a higher order factor structure that is different than a single order. If it's, I think the fact that we're using a single order higher order factor structure is probably what's causing us problems here. If it was, for example, the UPS P, you have 5 factors, right? And one of these is standalone. Then you have these 2 and these 2. That's the type of factor, higher order factor structure that could be tested. But a single order factor structure collapses to an equivalency of the correlations, it winds up being the same as the correlations, and so it doesn't work out. So anyway,
So no one's ever done one of those before? I feel like that's
oh no, this has been done. My guess is it's just not been done with the higher order single order factor structure, comparing it to the others. It must have to, like, mathematically they're the same, so it makes sense that you can't compare those. If we wanted to say, let's open this back up. If we wanted to say that we had F4 by F1 and F2 and F5 by F2 and F3, which is kind of weird. I think this is what I was trying to say would allow you to test differences. But M plus isn't liking it right now. Definitely you can have higher order factor structures, just FYI. Yeah, a single higher order factor winds up being the same as a correlation, so obviously that doesn't work out.
Well, I don't get why we would want to have one anyway, because it wouldn't change any of the relationships of the items to the original three, because it's just saying that the factors then are related, but you're looking at the items, not the factors.
Yeah, no. You have to think about it outside of the context of factor analysis. Maybe you want to have it because you want to be able to say that there is just that emotion regulation isn't really comprised of like three different things. That there's one thing that drives emotion regulation, and that it tends to drive these other three kind of facets of emotion regulation, and that you're going to use that one thing. Like if you think of the common thing that we think of, what's the common higher order factor in psychology? Everybody uses it to describe the higher order. What's that? G. Yeah. G. Yeah. And so G would be the higher order thing that's driving everything else, right? Yeah. I'm gonna have to come up with a better example, and we will do a better example next time, because this is gonna bug the shit out of me. All right. The last thing that I want to talk about today is the use of different types of estimators. So we've been using MLR, and MLR assumes something very specific about the distribution of your outcomes for your items. And what does anyone know what MLR assumes? Say that again. It's maximum likelihood, but it assumes that your outcomes, that your responses on your outcomes are, well, actually it doesn't matter if they're normally distributed or not with maximum likelihood, but it assumes that they're continuous, right? And this has, the ALS has a 4-item Likert type response: not at all, a little, somewhat, a lot. That's not a very continuous response scale, right? And so increasingly in psychology, we are running into problems with continuous response scales. And so we have developed a host of different types of estimators to handle those types of response scales. And for categorical response scales, we can specify that our variable is, our outcomes are categorical. And we can change our estimator to WLSMV. This is the weighted least squares maximum likelihood estimator. I don't know what the V stands for or why it's in there. But this will now change the response scale from continuous to probit, and that is moving up scales from a category of 1 to a category of 2 to a category of 3. And other than that change, everything else is roughly the same. So it might not allow you to correlate all 5 with all 6. see if it gives us an error message. No, it did. It allowed us to. All right, so we scroll down. We now see our univariate proportions and counts for each one of these categories. We get a chi-square model test. And we can see that when we've changed this now, some of our estimates look a little bit better, right? RMSEA looks a little bit worse. CLI and TLI, or CFI and TLI both look quite a bit better, right? SRMR is 0.032, and you don't need to worry about this. And then our model results, though, should be like roughly equivalent to what they were before. Still get standardized. Our correlations of factors are still like highly correlated. And then as we scroll down here, we still don't have any like ridiculous. These are roughly the same as they were before. The only real difference is being able to say we believe that these items are categorical or on a categorical response scale, and so we use WLSMV. WLSMV has the same issue that MLR does, and that is that you can't use traditional chi-square tests, but you can use that Satora-Bentler chi-square test for WLSMV. All right, that is it for today.
And you would run this in the presence of at least one set of categorical items.
Yeah, so if you have like a set of categorical and a set of non-categorical items, you can specify what's categorical and what's not categorical, but if you specify what's categorical, then your best option is to use WLSMV. You can use MLR with categorical variables, FYI. If you've specified them as categorical, MLR assumes by default that they're not, but if you specify them as categorical, you can still use MLR and you can still run it that way, and MLR will still work. I think it will. Huh. Covariances for categorical censored. Oh, yeah. So WLSMV will allow you to correlate categorical variables. MLR will not. And if you specify categorical with MLR, you're going to wait a little while because it takes a while for it to calculate. WLSMV goes a lot faster. It allows you to correlate. And if you read in the kind of M+ forums, Bengt and Lindig will talk about the importance of using WLSMV with categorical variables, that the estimates that you get are more accurate for WLSMV with categorical variables than MLR is. But technically, you can use MLR for both. And you still get roughly accurate or as accurate, but just not quite, I'm guessing. I'm not the type of person to run model simulations to compare an MLR to a WLSMV and determine which one of those is more accurate or less accurate. So, all right. Any other questions? While my model takes forever to run here. Okay, in the homework this week, it does say to compare a higher order factor structure. Obviously, don't do it. It's not going to work. Other than that, you can compare your factor structure to a single factor structure. Use the Satora-Bentler chi-squared difference test. Just Google Satora-Bentler chi-squared difference test calculator, and you'll find that web page, and then go from there. Otherwise, I will see you guys next week. So, all right, cool. Have a good weekend. Watch some